Right now, far beyond our cosmic neighborhood, there exists something so vast that it breaks intuition itself. A single galaxy so enormous that if it replaced the Milky Way, the entire night sky would simply disappear. Every star, every constellation, gone. This object is called IC 1101. It is not just bigger than our galaxy, it makes our galaxy look like a rounding error. By the end of this journey, you'll understand how something this massive can exist, what kind of monster lurks at its core, and why its very presence forces us to rethink how galaxies and the universe itself are built. But first, there's a question we think we understand, and almost never truly do. What is a galaxy, really? Let's begin. Right now, somewhere in the darkness beyond our cosmic neighborhood, something exists that should terrify you. A structure so impossibly massive that if we could place it where our galaxy sits, everything you've ever seen in the night sky would vanish. Consumed. Every star, every constellation, every neighboring galaxy gone. Swallowed whole by a cosmic predator that defies human comprehension. This monumental galaxy is called IC 1101. By the time we finish this journey together, you'll understand exactly why it holds the title of the largest galaxy we've discovered. You'll grasp how it achieved such an unthinkable size, what lurks in its core, and what its very existence reveals about the nature of the universe itself. But first, let's tackle something that seems obvious, yet remains incredibly difficult to truly absorb. What exactly is a galaxy? You've probably heard this word thousands of times. You know we live in the Milky Way galaxy. You've seen pictures of others floating in space. But when you really dig into it, what is a galaxy? At its most fundamental level, it's a colossal accumulation of stars, interstellar gas, cosmic dust, and a mysterious substance called dark matter, all held together by gravity's relentless grip. Imagine it like a cosmic city. Just as a city is a collection of buildings and people coexisting in the same area, a galaxy is a gathering of stars, planets, and everything else bound together in one enormous structure. The gravitational force of all that material prevents its components from scattering into the darkness of intergalactic space. But here's where the analogy breaks down. A city has clear boundaries. You know where downtown ends and the suburbs begin. You can point to its edge on a map. Galaxies aren't like that at all. They fade gradually into the blackness of intergalactic space, with no sharp border or defined edge. The density of stars simply decreases more and more as you move outward, until finally you reach the immense void between them. This makes measuring a galaxy's size surprisingly complicated, a point we'll return to when discussing IC 1101. Our own galaxy, the Milky Way, contains between 200 billion and 400 billion stars. It's an overwhelming number. If you could count one star per second, you'd need between 6,300 and 12,700 years just to enumerate all the stars in our galaxy. That time span is longer than all of recorded human history. Writing was invented barely 5,000 years ago. You could have started counting when the first humans began carving symbols into clay tablets, and you still wouldn't be anywhere close to finished. And yet, the Milky Way is considered an average-sized galaxy. Not especially large, not particularly small, just normal in the galactic context. When astronomers discovered this, it was humbling. Our galaxy, which seems so immense to us, is just one among billions of typical galaxies. Think about that. Everything humanity has ever known, every war fought, every love story written, every empire risen and fallen, all of it happened on one planet, orbiting one star among 300 billion stars in a completely ordinary galaxy. The Milky Way stretches across a diameter of approximately 100,000 light-years. This means if you traveled at the speed of light, the fastest anything can move it, would still take you 100,000 years to cross it from one end to the other. Light itself, the swiftest thing that exists in the universe, needs 100 millennia to complete that journey. Expressed in miles, our galaxy is roughly 588 trillion miles wide. That's a 5 followed by 14 zeros. Let me try to give that number some meaning. Imagine you could drive a car at highway speed, say 60 miles per hour, without stopping 24 hours a day, 7 days a week. It would take you approximately 1.12 billion years to cross our galaxy. The universe is only 13.8 billion years old. You'd need to drive for a time equivalent to 81 times the total age of the universe, just to traverse one fairly common galaxy. Can you feel your brain struggling with these numbers? Mine does. These figures are so colossal, they stop having meaning. We simply didn't evolve to comprehend distances of this magnitude. But here's what makes IC 1101 so extraordinary. Our galaxy, already astonishingly large by any human standard, is tiny compared to IC 1101. Absolutely tiny, like comparing a single house to an entire country. That's the difference in scale we're talking about. IC 1101 has an estimated diameter ranging between 4 million and 6 million light-years. Let me repeat that. Between 4 million and 6 million light-years. Our galaxy measures 100,000 light-years in diameter. IC 1101 is between 40 and 60 times larger than the entire Milky Way. In miles, that equals between 23 quadrillion and 35 quadrillion miles in diameter. A quadrillion is a 1 followed by 15 zeros. If you tried to cross IC 1101 at highway speed, it would take you approximately 460 quadrillion years. That number is so absurd, there's no coherent way to understand it. It's more years than there are atoms in your body. It's more years than seconds have passed since the Big Bang. It's a number that's simply unfathomable, impossibly large. But these numbers are real. This galaxy exists. It's out there right now. Colossal structure of stars, gas, and dark matter floating in the blackness of intergalactic space. If you have a powerful enough telescope and point it in the right direction, you can see it. It appears before our instruments as a faint, diffused smudge of light. An almost insignificant point to the casual observer, but one that actually represents a structure of truly astonishing scale. To put IC 1101's size in perspective, let's think about what would happen if we somehow replaced our galaxy with it. If IC 1101's center sat where the Milky Way's center currently sits, its outer edges would extend so far they would completely engulf the Andromeda galaxy. Andromeda is our closest large galactic neighbor. It sits about 2.5 million light-years away from us. To give you an idea of that distance, the light reaching us from Andromeda tonight left that galaxy when the first members of the genus Homo were just beginning to walk upright on the African savanna. Back in that distant era, our ancestors were still using simple stone tools, and modern humans wouldn't appear on Earth for another 2 million years. That's the magnitude of distance separating us from Andromeda. And IC 1101 would cover it without the slightest effort. IC 1101's magnitude is such that if it occupied our galaxy's place, it would extend far enough to completely swallow Andromeda and still have room to spare. The Andromeda galaxy, visible as a diffuse smudge to the naked eye on clear nights, would simply be assimilated by IC 1101's immense bulk. But it wouldn't stop there. It would also devour the Triangulum galaxy, another important member of our cosmic neighborhood. The Triangulum galaxy, located about 3 million light-years away, would be equally consumed. The Large Magellanic Cloud and the Small Magellanic Cloud, to dwarf galaxies that orbit our Milky Way like moons orbiting a planet, would be absorbed. They sit only about 160,000 and 200,000 light-years away, respectively. IC 1101 would engulf them without even noticing. In fact, IC 1101 would also consume most of the other galaxies in our local group. The local group is the galactic cluster that includes the Milky Way and about 50 other galaxies, all bound together by gravity. It extends approximately 10 million light-years across, and IC 1101, a single galaxy, exceeds half the size of our entire local group of galaxies. Stop and think about that for a moment. A single structure larger than a grouping of more than 50 galaxies. That's the scale we're dealing with. This isn't science fiction. This isn't exaggeration. This is observed reality. IC 1101 exists. Astronomers have measured it, photographed it, studied it for decades, and every measurement confirms the same terrifying conclusion. We've discovered something that shouldn't be possible, yet undeniably is. How does something this massive even form? What cosmic forces could build a galaxy 60 times wider than our own? What does it mean for our understanding of the universe that such titans can exist? These are the questions that haunt astronomers. Because IC 1101 isn't just big, it's a challenge to everything we thought we knew about galactic evolution. Every textbook assumption about how galaxies grow, how they interact, how the universe assembles its largest structures, IC 1101 pushes those assumptions to their absolute limits. And here's what should really unsettle you. IC 1101 is the largest galaxy we've found so far. But so far is the key phrase. The universe is incomprehensibly vast. We've barely scratched the surface of what's out there. Somewhere in the darkness beyond our cosmic horizon, there might be something even larger. Something that would make IC 1101 look small by comparison. The universe has a way of humbling us. Just when we think we've grasped the scale of things, we discover something that shatters our understanding completely. IC 1101 is one of those discoveries. It's a cosmic giant that forces us to expand our very notion of what's possible. And we're just getting started. We haven't even talked about what's inside this monster. We haven't discussed the supermassive black hole at its core, a predator so massive it makes the one in our galaxy look like a pebble. We haven't explored how IC 1101 grew to this size by devouring hundreds, possibly thousands of smaller galaxies over billions of years. The story of IC 1101 is a story of cosmic cannibalism, of gravitational violence on scales that defy imagination, of a universe far stranger and more terrifying than most people realize. But it's also a story about us, about our place in the cosmos, about how far we've come in understanding our universe, and how much further we still have to go. Because when you truly grasp the scale of IC 1101, when you really understand what we're looking at, something fundamental shifts in how you see reality. You start to realize that everything you've ever worried about, everything you've ever thought was important, it all happens on a tiny speck orbiting an ordinary star in an average galaxy that could be swallowed whole by structures like IC 1101 without even slowing down. Is that depressing? Maybe, but I find it liberating. Because if we're that cosmically insignificant, then we're also free to create our own meaning, to decide for ourselves what matters. The universe doesn't care what we do. That might sound harsh, but it also means we get to choose. And we've chosen to understand, to explore, to look out into the darkness and ask, what else is out there? That choice, that burning curiosity is what makes us human. It's what drove ancient peoples to map the stars, what compelled Galileo to build his telescope, what pushes modern astronomers to search for the largest structures in the cosmos. IC 1101 is an answer to that search. And the answer is more spectacular, more humbling, and more awe-inspiring than anyone could have imagined. Are you ready to go deeper? To explore not just what IC 1101 is, but where it is, how we found it, and what its existence means for the future of the universe itself? Then stay with me, because we're about to journey 1 billion light-years from home to visit the largest galaxy humanity has ever discovered. And I promise you nothing will look the same after this journey ends. Now that we've established the colossal scale of IC 1101, let's explore its location in the cosmos. Because where this galaxy sits in the universe is almost as mind-bending as its size. IC 1101 lies approximately 1 billion light-years from Earth. This distance is nearly as difficult to absorb as the galaxy's own dimensions. 1 billion light-years means that light, traveling at 186,000 miles per second, needs 1 billion years to cover that distance. Expressed in miles, IC 1101 sits about 588 quintillion miles away. That's a 588 followed by 18 zeros. There simply isn't an analogy that can make this distance tangible. It transcends any comparison with everyday experience. We must accept it as a number and move forward. But here's where it gets fascinating. The implications of this distance for observation are staggering. When we observe IC 1101 through our telescopes, we don't see it in its current state. We see it as it was 1 billion years ago. Let that sink in for a moment. The light reaching our instruments today left IC 1101 when the most complex life on Earth were single-celled organisms floating in primordial seas. Multicellular life existed, but only in its earliest stages. The Cambrian explosion, the moment when complex animal life first appeared on our planet, wouldn't occur for another 450 million years. There were no fish yet, no land plants, no insects. Dinosaurs wouldn't evolve for 770 million more years. Mammals wouldn't appear until 800 million years had passed. And humans wouldn't emerge for roughly 999 million years. When that light began its journey toward us, Earth would have been unrecognizable to a modern observer. The continents occupied completely different positions. The atmosphere had a different composition. The oceans teemed with primitive life forms that went extinct long ago. And somewhere in the depths of space, this galaxy was emitting light that would travel for 1 billion years before finally reaching the telescopes of a species that wouldn't exist for 999 million more years. Think about the absurdity of that. We're looking at ancient light, fossil light, light that's older than complex life on Earth. When you see an image of IC 1101, you're not seeing what's there now. You're seeing what was there when our planet was still figuring out how to build anything more complicated than slime. IC 1101 is located in the direction of the constellation Virgo, though sometimes it's also placed in Serpens, since it sits very close to the boundary between both. The exact border between constellations is somewhat arbitrary anyway, just lines drawn by humans to help us navigate the sky. The galaxy itself doesn't care which constellation we assign it to. IC 1101 is too faint to be seen with the naked eye. You need a telescope with an aperture of at least 8 to 10 inches to have any chance of locating it. And even then, it appears only as a blurry, weak smudge. It has an apparent magnitude of approximately 14.7, quite low by astronomical standards. For reference, the faintest stars visible to the naked eye under perfect conditions have an apparent magnitude of around 6. The magnitude scale is logarithmic, meaning each step represents multiplication rather than addition. An object with magnitude 14.7 is about 5,000 times fainter than the dimmest star you can perceive without optical aid. Even with access to a large amateur telescope, IC 1101 isn't a particularly impressive spectacle visually. It presents itself as a small smudge of diffuse light, barely distinguishable from the darkness of the background. The stunning images you may have seen of IC 1101 result from long exposure photography taken with professional equipment, images that accumulate light for many minutes or hours to reveal details invisible to the human eye. The galaxy was discovered on June 19, 1790, by British astronomer of German origin William Herschel. Herschel is one of the most important figures in the history of astronomy. Born in Hanover, in what is now Germany, he spent most of his professional life in England. He's the same astronomer who discovered the planet Uranus in 1781, the first planet found in the modern era. Herschel was a meticulous observer who dedicated countless hours to scrutinizing the night sky with his homemade telescopes. And when I say homemade, I don't mean he bought a kit from a store. Herschel polished his own mirrors by hand, a laborious process requiring enormous patience and skill. He spent hours polishing metal mirrors until they achieved the precise curvature necessary to focus the light of distant stars. His telescopes were among the best in the world at that time. His largest telescope had a 49-inch diameter mirror and a focal length of 40 feet. It was so big it became a tourist attraction. King George III of England came to see it. For decades, it was the largest telescope in the world. With these instruments, Herschel catalogued thousands of celestial objects, including galaxies, nebulae, and star clusters. He didn't know what many of those diffuse smudges of light actually were, but he observed them carefully and recorded their positions. His systematic method of observation laid the foundations for modern astronomy. When Herschel spotted IC 1101 in 1790, he had no idea what he was looking at. This happened more than a century before we understood that galaxies existed as separate island universes, distinct from our own Milky Way. Back then, the astronomical community considered those patches of diffuse light, which they called nebulae from the Latin word for cloud, to be simply clouds of gas or star clusters located within our own galaxy. The conception of a universe harboring billions of other galaxies, each with billions of stars, was an idea that wouldn't arrive for a long time. Herschel himself suspected that some of these nebulae might be other systems analogous to our Milky Way, but he couldn't prove it. The telescopes of his era lacked the power necessary to resolve individual stars in distant galaxies. To observers, they remained blurry patches of light, and their true nature constituted a profound mystery. This enigma persisted for more than a century, transforming into one of astronomy's great unanswered questions. By the early 20th century, astronomers had divided into two clearly differentiated factions. One group, headed by Harlow Shapley, maintained that spiral nebulae were relatively small clouds of gas within the Milky Way. The opposing side, led by Heber Curtis, argued they were island universes, vast stellar systems far beyond the confines of our galaxy. In April 1920, Shapley and Curtis met for what became known as the Great Debate, held at the Smithsonian Museum of Natural History in Washington, D.C. Each presented evidence supporting their position. Shapley pointed to measurements suggesting that some novae in spiral nebulae were too bright to be at extragalactic distances. Curtis countered with observations of dark dust lanes in edge-on spirals, similar to those we observe in our own galaxy. At the time, the debate was inconclusive. Neither astronomer had the decisive evidence needed to settle the question. That proof would arrive 4 years later. It wasn't until the 1920s that Edwin Hubble irrefutably demonstrated that many of these nebulae were actually separate galaxies, far beyond the Milky Way's limits. To do this, Hubble used the 100-inch Hooker telescope at Mount Wilson Observatory in California, which was then the largest in the world. His method relied on a special type of star known as a Cepheid variable to measure the distance to the Andromeda Nebula. Cepheid variables are stars that pulsate following a regular pattern, increasing and decreasing their brightness over periods spanning days or weeks. The crucial aspect of Cepheids is that a direct relationship exists between the duration of their pulsation cycle and their intrinsic brightness. A Cepheid with a longer period is intrinsically more luminous than one with a shorter period. This means if you can measure a Cepheid's period, you know its true brightness. And if you compare its true brightness with its apparent brightness in the sky, you can calculate how far away it is. In 1924, Hubble located Cepheid variable stars in the Andromeda Nebula. His measurements demonstrated that Andromeda was too far away to be part of our galaxy. It had to be a completely independent galaxy, situated about 900,000 light-years distant. Actually, his initial distance estimate was too low. Today, we know Andromeda lies about 2.5 million light-years away. Nevertheless, even his underestimated calculation was sufficient to prove his point. Andromeda definitely wasn't part of the Milky Way. This discovery completely transformed our understanding of the universe. Suddenly, the cosmos went from containing a single galaxy to harboring countless galaxies spread across unimaginable distances. The universe became immensely larger overnight, and humanity went from considering itself the center of everything to being a resident of an ordinary galaxy among billions. It's difficult to overstate how revolutionary this paradigm shift was. It's like waking up one morning to discover that what we believed was the entire world, our city, our country, everything known, was actually just one neighborhood within a metropolis with billions of other neighborhoods. That's a rough analogy for what happened to our cosmic vision in the 1920s. Before Hubble's finding, prestigious astronomers debated whether anything existed beyond the Milky Way. They knew the universe contained stars, and that the Milky Way was a vast collection of them. But the question of whether those diffuse nebulae were part of our galaxy or completely separate systems was a genuine uncertainty. The famous 1920 debate between Harlow Shapley and Heber Curtis was precisely about whether spiral nebulae were inside or outside our galaxy. Curtis defended that they were independent island universes, while Shapley insisted they were nearby gas clouds. Hubble's observations in 1924 settled the debate decisively. Spiral nebulae were indeed separate galaxies, incredibly distant, and each containing billions of stars. The universe wasn't a single galaxy, but countless galaxies distributed across distances that made even our Milky Way, with its 100,000 light-year diameter, seem small. And among all those countless galaxies, IC 1101 stands as one of the most extreme examples. It's a galaxy so colossal it defies our capacity for understanding, discovered more than a century before we even knew galaxies existed. The chronicle of recognizing IC 1101 as the largest known galaxy is itself a tale of how our technology and understanding have progressed over time. When Herschel first observed it, he saw nothing extraordinary just another faint, diffuse smudge among thousands. It was only with the arrival of modern telescopes and sophisticated measurement techniques that astronomers could determine its true distance and actual size. This brings us to an interesting question. What else exists out there that we haven't recognized yet? The universe is full of objects we've catalogued but still don't understand. There could be other galaxies even larger than IC 1101 hiding in plain sight in our astronomical databases. We simply haven't measured them carefully enough yet to know how extraordinary they are. The James Webb Space Telescope, launched in 2021, is already revealing details of distant galaxies that were previously impossible to see. Its infrared vision can penetrate the dust that blocks visible light, and its enormous mirror can capture light from incredibly faint sources. As we analyze its observations, we might discover galaxies that rival IC 1101 in size, or even surpass it. Ground-based telescopes are also experiencing significant improvements. The extremely large telescope, currently under construction in Chile, will have a 39-meter diameter mirror more than 4 times that of any existing optical telescope. It will be capable of seeing objects that are too faint to be detected today and resolving details that current telescopes cannot discern. The Vera Rubin Observatory, also located in Chile, will conduct, starting in 2025, the Legacy Survey of Space and Timer project that will photograph the entire visible sky every few nights for a decade. This initiative will generate the most complete map of the firmament ever created, cataloging billions of galaxies and potentially revealing structures whose existence we didn't know about. As our technology advances, our understanding of the universe expands in parallel. IC 1101 might be the largest galaxy we've found to date, but the key lies in that last temporal qualifier, because the universe is immense, and our exploration of it has barely begun. IC 1101 received its designation from the Index Catalogue of Nebulae and Star Clusters, which was published in the late 19th and early 20th centuries as a supplement to the earlier New General Catalogue. The Index Catalogue compilation was the work of John Louis Emil Dreyer, a Danish-Irish astronomer who worked at Armagh Observatory in Ireland. The galaxy appears as entry number 1101 in that catalogue, and to this day, most known galaxies and nebulae continue to be referenced by their NGC or IC designations. For decades after its discovery, IC 1101 remains simply one more entry in astronomical records. It was a blurry smudge among thousands of others, and nobody suspected its special nature. The technology to determine its real distance and size simply hadn't been developed yet. It wasn't until astronomers began measuring these properties that they realized how truly extraordinary this galaxy was. In 1964, a study of galaxies with radio sources observed that IC 1101 was among the diffuse elliptical galaxies under analysis, and that radio emissions were detected coming from it. These radio emissions in galaxies typically indicate the presence of active processes like material falling toward supermassive black holes. Later, in 1978, astronomer Alan Dressler conducted a detailed analysis of 12 rich galaxy clusters, one of which was Able 2029b cluster harboring IC 1101. The following year, in 1979, Dressler published a paper dedicated specifically to IC 1101, analyzing its dynamics and properties. His work unveiled the galaxy's unusual velocity dispersion profile, providing clues about its massive size and the enormous dark matter halo surrounding it. Since then, IC 1101 has been studied exhaustively with some of the most powerful telescopes ever built. The Hubble Space Telescope has captured detailed images of the galaxy's inner regions, while the Chandra X-ray Observatory has mapped the hot gas in the cluster enveloping it. Each new observation has provided more information about this extraordinary cosmic structure, confirming its status as one of the largest in the known universe. And here's what should unsettle you. We're looking at IC 1101 as it was a billion years ago. Whatever's happening there right now, stars being born, black holes devouring matter, civilizations rising and falling if they exist, we won't see for another billion years. The light showing us that future IC 1101 is already on its way. It's traveling through space right now, crossing the incomprehensible void between galaxies. But it won't reach Earth until long after our species might be gone. Long after the sun has expanded into a red giant and consumed the inner planets. Long after everything we've ever built has turned to cosmic dust. That's the brutal reality of cosmic distances. IC 1101 exists in our universe, but it exists in a different time. We're separated not just by space, but by the finite speed of light itself. In a very real sense, IC 1101 and Earth occupy different moments in cosmic history, and yet we can study it, we can measure it, we can understand it. That's the power of science. That's what makes astronomy not just a collection of facts, but a bridge across space and time, away for minds confined to one tiny planet to reach out and touch the deepest mysteries of existence. IC 1101 is out there right now, a billion light years away, impossibly vast, impossibly old, impossibly distant, and somehow, against all odds, we found it, we measured it, we named it. That might be the most human thing we've ever done. To better understand IC 1101's history and how it became so enormous, we need to analyze what type of galaxy it is. Because galaxy classification isn't just academic labeling, it tells us about evolution, about cosmic life cycles, about the forces that shape the universe itself. Astronomers classify galaxies into different types based on their shape and structure. This classification system was first developed by Edwin Hubble in the 1920s and has been refined over the decades. But here's what you need to understand. These aren't just categories. They're stages in a cosmic story that spans billions of years. The first type are spiral galaxies, those classic pinwheel-shaped beauties you've probably seen in photographs. They have a flat disk with spiral arms extending outward from a central bulge. Our Milky Way is a spiral galaxy, specifically a barred spiral because it has a bar-shaped structure in its center. The Andromeda Galaxy is also a spiral, though not barred. Spiral galaxies contain large amounts of gas and dust and are actively forming new stars, especially in their arms. The spiral structure itself is a density waiver pattern that moves through the disk and triggers star formation as it passes. These are the vibrant, living galaxies of the universe. Young, dynamic, still creating. The second type are elliptical galaxies, rounder or elongated in morphology, similar to a three-dimensional oval or a football. Their shape can vary from almost spherical to very elongated. Unlike spirals, ellipticals contain very little gas and dust, and most have ceased forming new stars or do so at a very low rate. The stars in elliptical galaxies tend to be older, giving them a reddish or yellowish coloration compared to the bluer tone of spirals. These are the old, dying galaxies, the cosmic retirement homes where stars slowly fade into darkness. The third type consists of lenticular galaxies, an intermediate form between spirals and ellipticals. They have a disk like spirals and often a central bulge, but they lack the spiral arm structure. Sometimes they're described as spiral galaxies that have lost their arms. Lenticular galaxies are frequently found in dense environments, like galaxy clusters, where interactions with other galaxies and hot gas may have stripped away the gas necessary for star formation and maintaining spiral structure. There are also irregular galaxies that don't fit clearly into any of these categories. They present chaotic shapes without defined structure, like the large and small Magellanic Clouds. They're often smaller galaxies that have been distorted by gravitational interactions with larger neighbors or are in the process of merging. Some astronomers also recognize a fourth category called peculiar galaxies. These are stellar systems with unusual characteristics that distinguish them from normal types. A galaxy might be classified as peculiar if it has distorted spiral arms, anomalous jets emanating from its center, or layers and rings of stars indicating past interactions. Many peculiar galaxies are the result of recent or ongoing galactic mergers. And here's where things get interesting for IC 1101. Although galaxy classification might seem like simple academic categorization, it actually tells us enormous amounts about evolution. The different types of galaxies represent different stages in the cosmic life cycle. Spiral galaxies are generally younger with active star formation, while ellipticals are usually older, having already surpassed their star-forming stage. Giant elliptical galaxies, like IC 1101, represent the extreme endpoint of galactic evolution. Massive structures formed over billions of years of mergers and growth. Understanding what type of galaxy IC 1101 is helps us understand its history and its future. IC 1101 is classified as a supergiant elliptical or supergiant lenticular galaxy. Astronomers aren't entirely sure which classification is more accurate because it sits right at the boundary between these two types. When classifying a galaxy, astronomers use the designation E for ellipticals and SO for lenticulars. Consequently, IC 1101 is classified as E0, indicating it could belong to either category. If it were a lenticular galaxy, our perspective might be showing it at its broadest dimensions, which would give it a more spherical appearance than it actually possesses. Lenticular galaxies are flattened disks, so when observed edge-on, they resemble a line, while viewed face-on they appear circular, and from an intermediate angle they adopt an elliptical shape. It's possible IC 1101 is one of these lenticular galaxies that we happen to observe, face-on or nearly face-on. However, the consensus among astronomers is that IC 1101 is a CD-type galaxia-specific classification reserved for the most massive. The lowercase c indicates it's a supergiant, the largest galactic size category, and the uppercase D means it's enveloped by a vast halo of diffuse light extending far beyond its main body. Some experts interpret CD as central dominant, since these cosmic objects are almost invariably located at the cores of galactic clusters, where they exert gravitational dominance. Others adhere to the original meaning from the classification system, where C represents supergiant and D alludes to the diffuse halo. Whatever the interpretation, the fundamental point is that CD galaxies are the most colossal among the colossal, the most massive in the universe. These galaxies are typically found at the hearts of clusters, which is precisely IC 1101's location. Residing at the center of a massive cluster known as Abell 2029, its position at the cluster's core isn't a coincidence. It reached that location and grew to its disproportionate size through processes we'll analyze shortly. But first, let's talk about something that might surprise you: color. The color of a galaxy reveals to astronomers enormous amounts of information about the internal processes occurring within it. Because different types of stars emit light of different colors, hot stars generally young and massive, shine with bluish light, while cool stars, usually older and smaller, emit red or yellow glow. Galaxies with blue tones are typically in the throes of star formation. When new stars are born from clouds of gas and dust, the most massive and hot among them give off blue light. These massive blue stars consume their fuel at a breakneck pace, with lives lasting only millions of years instead of billions. Therefore, a large amount of blue light coming from a galaxy indicates active stellar birth. Since blue stars don't live long enough to be observed unless they formed recently, they're the candles that burn bright and fast, illuminating the cosmic nurseries where they're born. In contrast, galaxies with red or yellow tints are usually ancient and quiet. They've exhausted most of their gas and dust, so new star formation is very scarce. The stars that endure are older, cooler, and smaller. The massive blue stars that once existed burned out long ago. What remains are the smaller, cooler stars that have been shining for billions of years, granting the galaxy its reddish or yellowish appearance. These are the cosmic embers, the last dying light of galaxies that have run out of fuel. IC 1101 presents a markedly yellowish-red color, telling us it's an ancient galaxy that has largely ceased its star formation activity. In a sense, it's extinguishing not dramatically or suddenly, but slowly over billions of years as its remaining stars age and eventually go dark without new ones being born to replace them. Astronomers sometimes refer to galaxies like IC 1101 with the term red and dead, alluding to their color and absence of active star formation. Though it sounds dramatic, it's a slow process. The stars currently inhabiting IC 1101 will continue shining for trillions of years. However, as each star extinguishes, no new one is born to occupy its place. This is what makes IC 1101 so haunting. It's not dying violently. It's fading quietly into cosmic darkness, one extinguished star at a time. Once we've established IC 1101's scale, it's time to examine how this cosmic titan formed. No galaxy is born a supergiant elliptical. These massive galaxies are forged over billions of years through a process astronomers call galactic cannibalism, and understanding this mechanism is fundamental to grasping how IC 1101 grew to its current state. Galaxies aren't static objects, floating motionless in space. They move through the cosmos, propelled by the gravitational attraction of other galaxies and the large-scale structures surrounding them. The universe is filled with invisible streams and flows of gravity generated by the distribution of matter, both visible and dark. And galaxies move along these gravitational currents like leaves in a river. When two galaxies approach close enough, their mutual gravitational attraction begins to deform them. Tidal forces stretch the galaxies, tearing stars and gas from their normal positions and extracting long streams of material that create structures known as tidal tails. These interactions can trigger intense bursts of star formation as gas clouds are compressed due to gravitational chaos. If the galaxies move slowly enough relative to each other and pass close enough, they can become gravitationally bound, and at that moment, merger becomes inevitable. The two galaxies initiate a complex gravitational dance that can last hundreds of millions of years, orbiting around each other and passing through repeatedly. With each pass, they lose energy due to gravitational friction, and their orbits decay until they finally merge into a single larger galaxy. When two spiral galaxies collide, the result is usually an elliptical galaxy. The ordered rotation of stars in spiral disks is disrupted by gravitational chaos, and stars that once followed circular paths are thrown into chaotic, random orbits. Gas clouds collide and either form stars or heat up and are expelled from the merging galaxies. The central supermassive black holes of both galaxies spiral inward and eventually merge, creating a single even more massive black hole. When the dust settles, what remains is an elliptical galaxy. The organized spiral structure has been destroyed, replaced by a more chaotic ellipsoid shape, and stars orbit the center of the resulting galaxy following random trajectories, giving it its rounded appearance. IC 1101 reached its current size through countless mergers of this type over billions of years. Astronomers estimate it has experienced at least 10 major mergers and possibly many more. Each merger added mass to the galaxy, increasing its size and gravitational influence. It also depleted its gas reserves, as collisions either triggered star formation that consumed it or expelled it into intergalactic space. This is why IC 1101 is now virtually devoid of the gas necessary to form new stars, occupying its privileged place at the heart of the Able 2029 cluster, which contains thousands of other galaxies. IC 1101 has become the ultimate predator over cosmic eons. The most massive object within a galactic cluster tends to sink toward the central region, dragged by a process known as dynamical friction. As a massive galaxy moves through the cluster, its gravitational field attracts the surrounding dark matter and galaxies. This attraction generates a gravitational wake behind it, much like a ship leaves as it navigates. That wake exerts a drag force that slows the galaxy, decelerating its advance. The slower galaxies inevitably fall toward the cluster's center. This is why the most massive galaxies usually end up at the core, regardless of their initial position. Once established there, their growth continues by consuming any smaller galaxy that ventures too close to their reach. The cluster environment provides a constant supply of victims for this process. Smaller galaxies that wander and fall under the gravitational dominion of the central giant are dismembered. This phenomenon, for obvious reasons, sometimes receives the name galactic cannibalism. In essence, the larger galaxy devours the smaller ones, absorbing their stars and dark matter while stripping them of all their gas. Tidal forces are what tear apart these smaller galaxies. Their stars end up scattered, integrating into the central galaxy's halo. Over billions of years, the evidence of these individual mergers gradually erases itself. The stolen stars settle into new orbits until they become indistinguishable from the dominant galaxies. Original stellar population. IC 1101 has been repeating this cycle for eons. Every smaller galaxy that has approached too closely has been consumed, and its material has been incorporated into IC 1101's growing structure. This explains why the galaxy possesses such an extraordinarily vast, diffuse, stellar halo extending far beyond its core. That halo is composed of stars that once belonged to other galaxies that no longer exist as separate entities because they've been completely assimilated by IC 1101. Let's now analyze IC 1101's stellar population, as it offers another perspective for understanding its immensity. Astronomers calculate that IC 1101 contains approximately 100 trillion stars. This figure equals 100,000 billion stars, a number written as a 1 followed by 14 zeros. 100 trillion stars. And each one is a sun in its own right. In comparison, our Milky Way harbors between 200 billion and 400 billion stars, using an average estimate of 300 billion. IC 1101 contains around 330 times more stars than our entire galaxy. If you remember the counting exercise, counting IC 1101's stars at a rate of 1 per second would require 3.2 million years. This is a period 10 times longer than our species' existence. Think about the meaning of these numbers. Each of those 100 trillion stars is a sun. Some are larger than ours, while others are smaller. Some are hotter and bluer, burning their fuel rapidly in a fleeting display of glory. Others are cooler and redder, burning slowly for trillions of years. Each star has its own story, its own evolution, and its own final destiny. And many of these stars don't travel alone. Binary star systems, where two stars orbit each other, are very common in the universe. There are also triple systems, and even more complex multiple-order systems. Within IC 1101, there could be tens of trillions of binary systems, each immersed in an intricate gravitational dance maintained for billions of years, most likely harbor planets in their orbits. Thanks to exoplanet studies, we now know planetary systems are the norm, not the exception. Most stars have at least one planet, and many possess several. If IC 1101 follows this same trend, there could be hundreds of trillions of planets in this single galaxy. Hundreds of trillions of worlds, each with its particular geology, its own atmosphere or lack thereof, and a history extending billions of years. Some might be scorched rocks very close to their stars. Others could be gas giants, similar to Jupiter, with turbulent atmospheres and dozens of moons. Others could be frozen worlds in the outermost regions of their solar systems. And some, perhaps a considerable number, could be rocky worlds situated in the habitable zone of their stars, where water could exist in liquid state on the surface. Could any of those worlds harbor life? The answer is we simply don't know. However, from a statistical standpoint, with such quantities of stars and planets, it seems almost inconceivable that at least some don't possess the ideal conditions for life as we conceive it. The chemistry of carbon-based life in liquid water isn't particularly exotic. Its ingredients are abundant throughout the cosmos. With hundreds of trillions of opportunities, it seems almost inevitable to think some of those worlds have developed life. Whether that life has achieved intelligence is a completely different question. Life on Earth existed for almost 4 billion years before intelligence emerged, and even after, millions of years were necessary for that intelligence to develop to the point of allowing us to build telescopes and contemplate distant galaxies. Intelligence could be a common phenomenon in the universe, or it could be extraordinarily rare. We still don't have the answer, but in some corner of IC 1101, orbiting one of those 100 trillion stars, there could be beings observing us. Beings who have built their own telescopes and discovered their own distant galaxies. Beings who, like us, wonder if they're alone in the universe. The light from our galaxy has traveled for 1 billion years to reach there. If they receive it, they'll see us as we were 1 billion years ago, when life on Earth was just beginning to experiment with multicellularity. From their perspective, they'd be analyzing light 1 billion years old. They'd see an Earth that only harbored single-celled organisms and primitive multicellular life forms. They'd have no way whatsoever of knowing what we've become since then. And we have no way of knowing what's happening there right now. The distance doesn't just separate us in space, separates us in time. We're looking at IC 1101's past. Any civilization there is looking at our past. We're two ships passing in the cosmic night, forever separated by the cruel mathematics of distance and the speed of light. That's the tragedy and the beauty of the universe. It's filled with wonders we can observe but never touch, with worlds we can imagine but never visit, with stories we can ponder but never truly know. IC 1101 exists. It's real. It's out there right now. But it might as well be in another universe entirely, for all the difference it makes to our daily lives. And yet, knowing it exists changes everything. At the heart of IC 1101 lurks something truly extraordinary. Something so massive and so powerful that it shapes the entire galaxy surrounding it. I'm talking about a supermassive black hole, and this isn't just any supermassive black hole. This is one of the most colossal black holes ever discovered, an authentic cosmic monster whose scale defies easy comprehension. Black holes are essentially regions of space where gravity reaches such extreme intensity that absolutely nothing can escape their dominion. Not even light itself has the capacity to evade their pull. These objects originate when a quantity of matter is compressed into a sufficiently small volume, causing gravitational force to become overwhelming and irresistible. Once you cross a black hole's boundary, a demarcation known as the event horizon, no possibility whatsoever of return exists. The fall toward the center becomes inexorable. In this process, matter is stretched and torn apart by intense tidal forces. The final destiny is being crushed to annihilation in the singularity residing at the black hole's very heart. There are several categories of these enigmatic objects. One corresponds to stellar mass black holes, which form when large stars collapse at the end of their existence. These celestial bodies usually possess masses ranging between 5 and 50 times our Sun's mass. They're a common phenomenon throughout the universe, the remnants of extinct stars scattered across every galaxy's immensity. Then we find intermediate mass black holes. Their masses span from hundreds to thousands of solar masses. These are considerably rarer and shrouded in greater mystery. Scientists don't fully comprehend their formation process. Some hypotheses suggest they could result from stellar mass black hole mergers over time. Other theories propose they might have originated through completely different processes. Finally, there exist supermassive black holes. These are the true cosmic giants, with masses ranging from millions to billions of times our Sun's mass. They're located at the centers of most large galaxies, including our own Milky Way. The exact mechanism of their formation remains an area of very active research. It's possible they grew from smaller black holes through mergers and accretion during billions of years. Alternatively, they could have formed through other mechanisms in the early universe that we still don't completely understand. The black hole situated at the Milky Way's center receives the name Sagittarius A star, often abbreviated that way. It contains approximately 4 million solar masses. This means its mass is 4 million times greater than our Sun's. The figure certainly sounds enormous, and it is. All that mass is concentrated in a region of space smaller than our solar system. However, compared to the black hole at IC 1101's center, Sagittarius A star is almost insignificant. The analogy would be like comparing a marble to a large boulder. The supermassive black hole in IC 1101's heart is estimated to contain between 40,000 and 100,000 million solar masses. Different measurement methods yield different results. For this reason, some uncertainty exists about its exact value. But even the most conservative estimates place it among the most massive black holes known. If we use 60,000 million solar masses as a middle estimate, this implies IC 1101's black hole is approximately 15,000 times more massive than the one at our galaxy's center. 15,000 times more massive. If Sagittarius A star is already impressive, and it certainly is, then IC 1101's black hole reaches an almost incomprehensible level. This object is catalogued as PKs 1508 plus 059, a name derived from its celestial coordinates. It's a bright radio source, indicating it emits significant quantities of radio waves we can detect with radio telescopes. These radio emissions come from matter falling toward the black hole and being accelerated to prodigious velocities. When matter plunges toward a black hole, it doesn't fall directly in a straight line. Instead, it spirals inward, forming a disk of material called an accretion disk. As this material swirls, friction heats it to colossal temperatures, causing it to shine across the electromagnetic spectrum. The innermost disk regions can reach temperatures of millions of degrees, hot enough to emit X-rays. Some of this material is expelled along the black hole's poles in the form of jets. These jets are flows of particles accelerated to speeds near light's velocity that project into space along thousands or millions of light years. The mechanism generating these jets isn't fully understood, but it's known to involve the interaction between the black hole's intense gravity, its rotation, and magnetic fields threading through the accretion disk. The black hole at IC 1101's center produces two of these jets, which are visible at radio wavelengths. These extend far beyond the galaxy's visible portion, injecting energy into the surrounding intergalactic medium. They represent one of the universe's most powerful phenomena, with the capacity to affect gas in entire galaxy clusters. The relationship between a galaxy's size and its central black hole is a well-established fact in astronomy. Larger galaxies tend to harbor larger central black holes. This correlation is so consistent that astronomers believe a fundamental connection must exist between galaxies' growth and their black holes' growth. This makes sense when considered in the context of galactic mergers. When two galaxies merge, the black holes at their centers eventually meet and also merge. This process takes time, perhaps hundreds of millions of years after the galaxies themselves have combined. The black holes spiral around each other, losing energy through gravitational radiation until they finally unite into a single, more massive black hole. Therefore, as IC 1101 consumed other galaxies over billions of years, it was also consuming their central black holes. Each merger added mass not only to the galaxy, but also to the black hole at its core. The result is a black hole of magnitude proportional to the enormous size of the galaxy harboring it. It's calculated that the black hole at IC 1101's center is accreting or consuming material equivalent to about 450 solar masses each year. This means annually it adds to its mass the equivalent of 450 suns, a process that has continued for billions of years. This accumulation adds up to an incredible amount of material. Nevertheless, even this enormous accretion rate is barely a trickle compared to the black hole's total mass. At this rate, more than 100 million years would be needed to add just 1% to its mass. The black hole grew much faster in the past when more material was available to consume. Currently, it finds itself in a relatively quiescent state, slowly increasing its already immense volume. There's something truly awe-inspiring about contemplating a black hole of this size. Its event horizon, the boundary beyond which nothing can escape, is simply enormous. The event horizon's size depends directly on its mass. A black hole of 60,000 million solar masses would have an event horizon with a radius of approximately 285 billion kilometers. This distance is more than 1,800 times the separation between the Sun and Earth. Earth's entire orbit around the lunar journey of 590 million miles would fit inside this black hole's event horizon nearly 900 times. If this colossal cosmic entity were situated in our solar system with its center at the Sun's position, its event horizon would extend far beyond Pluto's orbit. Neptune, Uranus, Saturn, Jupiter, Mars, Earth, Venus, and Mercury, all of them, would lie within it. The entire known solar system would be contained within the black hole's gravitational domain. Having already surpassed the point of no return, this object's mass and gravity affects the entire galaxy surrounding it. Stars in IC 1101's central regions rotate around this black hole at prodigious velocities, maintained in their orbits by its immense gravitational attraction. The velocity dispersion of stars in the galaxy, measure of how rapidly stars move in random directions, increases toward the center as the black hole's gravitational influence becomes dominant. IC 1101 also possesses the largest galactic core ever measured. A galaxy's core is the dense central region where stars cluster most closely. In most galaxies, this core is relatively compact, but IC 1101's is different. A 2017 study based on Hubble Space Telescope images revealed that IC 1101's core has a radius of approximately 4,200 parsecs, equivalent to about 14,000 light-years. That dimension is larger than many small galaxies in their entirety. The Large Magellanic Cloud, a major dwarf galaxy orbiting our Milky Way, measures only about 14,000 light-years in diameter. IC 1101's core alone is comparable in size to entire galaxies. This unusually large core is believed to have been carved out during galactic collisions when black holes merge. The gravitational dynamics can fling stars out of the core region through a process known as gravitational slingshot. As two supermassive black holes spiral closer, they interact gravitationally with nearby stars. These interactions can accelerate stars to high velocities, ejecting them from the core toward the galaxy's outer regions. Each merger IC 1101 experienced would have ejected stars from its center. Over billions of years and numerous mergers, a significant fraction of the core's original stellar population has dispersed toward the halo. This is why the core is so extensive and relatively diffuse compared to other massive elliptical galaxies. The mass deficit in IC 1101's core is estimated at about 490,000 million solar masses. This means material equivalent to 490,000 million stars has been ejected from the core throughout the galaxy's history, scattering to outer regions or even into intergalactic space completely. The figure of 490,000 million solar masses exceeds many galaxies' total mass. IC 1101 has expelled from its core more material than most galaxies contain in their entirety. Now, let's broaden our perspective to examine IC 1101's cosmic environment, the Abell 2029 galaxy cluster. Understanding this cluster helps us understand how IC 1101 grew to such monstrous size and what role it plays in the broader cosmic structure. Galaxy clusters are precisely what they sound like: collections of galaxies bound by their mutual gravitational attraction. They count among the largest gravity-bound structures in the universe. Although larger formations exist like superclusters and cosmic filaments, these aren't gravitationally bound. In fact, they're being torn apart by the universe's expansion. Galaxy clusters, by contrast, are large enough that their own gravity resists this expansion, maintaining them coherent throughout cosmic time. The Abell 2029 cluster contains thousands of individual galaxies, all orbiting around a common center of mass. It was first catalogued by George Abell in 1958 as part of his exhaustive catalogue of galactic clusters. Abell used photographs from the Palomar Observatory Sky Survey to identify and classify more than 4,000 clusters, creating a resource astronomers still use today. This cluster lies about 1 billion light-years away in the direction of the Virgo constellation. Its diameter sits between 5.8 and 8 million light-years. It's an enormous structure larger than the distance between our Milky Way and the Andromeda Galaxy. The cluster is one of the most massive in our cosmic neighborhood and has been studied extensively. X-ray observations reveal it's in a remarkably relaxed state, indicating it hasn't experienced a major merger with another cluster in recent cosmic history. This state of quietude allows astronomers to make precise measurements of its mass distribution and dark matter content. Able 2029's total mass is estimated at around 100 trillion solar masses. IC 1101 at its center contributes a significant fraction of that mass. The cluster's galaxies move at velocities up to 8,700 miles per second, maintained in their orbits by the combined gravity of visible matter and dark matter. And here's what should terrify you about dark matter. Observations from the Chandra X-ray Observatory suggest something disturbing. If Able 2029 is a representative sample of the universe, then between 70 and 90% of all universal mass consists of dark matter. This conclusion is coherent with other measurements obtained through different methods, like analyzing the cosmic microwave background, radiation, and studying large-scale galaxy distribution. The amount of dark matter in the Able 2029 cluster is estimated to equal more than 100 trillion solar masses. It's an almost inconceivable quantity of matter mostly invisible. It's this mass that keeps the cluster bound and molds the disposition of visible galaxies and hot gas within it. For perspective, this mass equals approximately 500 Milky Way-like galaxies, all in the form of undetectable dark matter. This dark matter forms an immense halo that envelops and permeates the cluster, providing the gravitational scaffolding that coheres everything together. Without its presence, the cluster's galaxies would move at velocities too high to remain gravitationally bound. They'd scatter and drift away from each other into intergalactic space. It's precisely dark matter that keeps them united. And IC 1101 sits at the absolute center of this invisible web, the spider, at the heart of a gravitational trap spanning millions of light years. The galaxy didn't arrive there by accident. It earned that position through billions of years of cosmic violence, devouring everything that came too close, growing larger with each kill until it became the undisputed master of its domain. And it's still feeding, still growing, still consuming anything foolish enough to wander into its gravitational reach. That's the reality of IC 1101. It's not just the largest galaxy we've found. It's a cosmic predator that's been hunting for billions of years, and it's nowhere near finished. Now that we've explored IC 1101's mind-shattering dimensions and violent history, a question emerges. If this galaxy is so colossal, harboring 100 trillion stars and extending across millions of light years, why isn't it more famous? Why does it remain obscure outside astronomical circles? The answer reduces to two fundamental factors: distance and surface brightness. IC 1101 sits 1 billion light-years away from us. It's an almost unimaginable distance. Although the galaxy itself is gigantic, its remoteness causes it to appear tiny from our perspective. The effect resembles how a mountain seems small when observed from great distance. The mountain hasn't changed size, but it occupies a very small angle in our field of vision. Due to this remoteness, IC 1101 in its entirety occupies an angular size of approximately 1.2 by 0.6 arcminutes. An arcminute equals 1/60th of a degree. For comparison, the full moon presents an angular size of about 30 arcminutes, half a degree. This means IC 1101 appears between 25 and 50 times smaller than the moon viewed from Earth. If you held a small coin at arm's length, It would cover a portion of sky several times larger than IC 1101 occupies. This colossal galaxy, large enough to engulf our entire local group, appears smaller than a coin held at distance. But angular size isn't the only determining element. We must also consider surface brightness. This concept refers to the amount of light an object emits per unit area in the sky. A galaxy can be intrinsically very luminous, emitting a formidable total amount of light. Nevertheless, if that light distributes over a very extensive area, its surface brightness can be quite low. IC 1101 is indeed intrinsically very luminous. It's one of the brightest galaxies known, shining with the light of trillions of stars. The problem is, all that luminosity spreads across an immense volume of space. The result is a galaxy with relatively low surface brightness, making it appear as a faint, diffuse object even to large telescopes. The galaxy presents an apparent magnitude of approximately 14.7, making it about 5,000 times fainter than the dimmest stars visible to the naked eye. You need a telescope with an aperture of at least 8 to 10 inches to have any chance of locating IC 1101. Even with such an instrument under exceptional dark sky conditions, the galaxy isn't particularly spectacular to view. It manifests as a faint, diffused smudge of light, barely distinguishable from the celestial background's darkness. The stunning images of IC 1101 that circulate are actually products of long-exposure photography. When astronomers seek to capture subtle details in distant galaxies, they don't simply point their telescope and take a snapshot. Instead, they expose the camera sensor to light for minutes or hours, allowing photons to accumulate progressively. What awaits IC 1101 in the future? Predicting anything's future on cosmic timescales is inherently uncertain, but we can formulate some grounded conjectures based on our understanding of physics and galactic evolution. IC 1101 will likely keep growing, at least for a while. While smaller galaxies exist in its vicinity, it'll continue devouring them. The Able 2029 cluster harbors numerous potential victims, galaxies that will eventually fall into IC 1101's gravitational embrace and be absorbed. This galactic cannibalism process will extend for billions of years. Each assimilated galaxy adds its stars to IC 1101's already colossal mass. Each merger brings more dark matter, increasing the galaxy's gravitational dominion over its environment. However, this growth can't perpetuate indefinitely. A moment will arrive when IC 1101 runs out of galaxies to consume. The cluster possesses a limited number of members, and as the largest devours the smallest, fewer and fewer remain. The universe's expansion also plays a crucial role. The universe isn't static. Space itself expands, driving galaxies apart from each other. Galaxies currently beyond IC 1101's gravitational reach will move increasingly farther away with cosmic time's passage. Within the Able 2029 cluster, the gravity cohering everything is strong enough to resist this expansion. The cluster will maintain coherence with its members bound by mutual gravitational attraction, even while the universe around it expands and other galactic clusters vanish into distance. Over trillions of years, the stars inside IC 1101 will age and die. Without new star formation to replace them, the galaxy will gradually dim. First, the most massive and brilliant stars will extinguish, as has already occurred. Then, medium-sized stars like our Sun will exhaust their fuel, expanding into red giants before collapsing into white dwarfs. Finally, even small red dwarfs, capable of burning for trillions of years, will eventually deplete their hydrogen and fade away. What remains will be a dark galaxy, a vast collection of stellar remnants drifting through space. White dwarfs will slowly cool toward absolute zero, their faint light vanishing over trillions of years until they become cold black dwarfs. Neutron stars will spin increasingly slower, their magnetic fields decaying and rotation slowing. Stellar mass black holes will wander through darkness, occasionally absorbing any remnant approaching too closely. The supermassive black hole at the center will endure much longer. A black hole of 60,000 million solar masses will take an unfathomable time to evaporate through Hawking radiation. We're talking about timescales of 10 to the power of 100 years or even more. Numbers so enormous they make the universe's current age seem like a mere blink. But even this timescale is finite. With sufficient time, even the most massive black holes will eventually evaporate. IC 1101's last vestige will disappear in a final burst of Hawking radiation, leaving behind nothing but a scattering of fundamental particles adrift in a perpetually expanding and cooling universe. This is the final destiny awaiting not only IC 1101 but all galaxies, including our own Milky Way. The universe heads very slowly toward a final state of maximum entropy where nothing interesting can ever happen again. And here's what you need to understand about IC 1101's existence. When you truly grasp what we're looking at, when you really comprehend that a single structure contains 100 trillion stars, that it's so massive it could swallow our entire galactic neighborhood, that it's been feeding and growing for billions of years, something fundamental shifts in how you perceive reality. You start to realize that everything you've ever worried about exists on a tiny speck orbiting an ordinary star in an average galaxy that could be consumed whole by structures like IC 1101 without even slowing down. IC 1101 is out there right now, a billion light years away. Impossibly vast, impossibly old, impossibly distant, and somehow, against all odds, we found it. We measured it. We understand it. That might be the most extraordinary thing of all.